We are now ready to consider the bonding and the stereochemistry in disaccharides. Okay, so as I said in the intro to sugars, disaccharides are when you have two monosaccharides linked together through a glycoside bond, which is of course what we considered in the previous lesson. So what I consider the simplest case of a disaccharide would be maltose, which is when you have two glucoses linked together in what I call the head-to-tail arrangement. Okay, so we have maltose drawn here in both the Haworth projection and in the cyclohexane chair conformation. And what you can see from the numbering of the carbons in the Haworth projection is on the left-hand sugar, the linkage occurs at carbon 1, which is what the anomeric carbon and what I call the head of a sugar. And on the right-hand glucose, the linkage is occurring at carbon 4, which being the furthest carbon in the ring from carbon 1 is what I call the tail of the sugar. Okay, so in this case, in forming the glycoside bond, the C4OH on the right-hand glucose is a nucleophile that comes in and attacks the anomeric carbon, C1, on the left-hand sugar. Okay, so just like we saw methanol as a nucleophile for forming glycosides in the previous lesson, we're now just using the C4OH of glucose as the nucleophile in the same way. Okay, so it will be an exercise for you to actually come up with the mechanism of this. In terms of the stereochemistry, at the anomeric carbon of the left-hand sugar, the second glucose is occupying the alpha position. Okay, it's down below the mean plane of the left-hand glucose. So therefore we say that the stereochemistry at the glycoside bond is alpha. But we also, in this case, need to consider the stereochemistry at the terminal anomeric carbon on the right-hand sugar, C1 of the right-hand sugar. And as you can see from looking at the chair conformation, that OH is occupying an equatorial position. So therefore, the stereochemistry here is beta. It's also clear to see from the Haworth projection the cis relationship between the OH on C1 and the CH2OH coming off of C5 on the right-hand sugar, and then the trans relationship between the acetal on C1 and the CH2OH coming off of C5 on the left-hand sugar, indicating the alpha linkage of the glycoside bond. Okay, so that's maltose. Now moving to one level of complexity higher, we need to talk about sucrose. Sucrose, of course, is table sugar, and it consists of a molecule of glucose and a molecule of fructose. But in this case, instead of the two monosaccharides being coupled head to tail, they're actually coupled head to head. And what I mean by that is anomeric carbon to anomeric carbon through the acetal oxygen. Okay, so the anomeric carbon in the case of the fructose, which is on the right side, is C2 because it is a ketose. Now, what you should notice immediately from looking at these structures is glucose is in its ordinary pyranose form, but fructose is in the furanose form. And specifically, fructose has to be in the beta-furanose form in order to form sucrose. We know that fructose is beta over here because what we have to do is look at the relative stereochemistry of the oxygen on C2 with the CH2OH on C5. It is still the CH2OH on C5 is still what we consider, even though it's a furanose, and they are, as you can see, cis to each other, which is how we know that it is beta. Okay, so at equilibrium, it turns out fructose is 57% beta pyranose, 31% beta furanose, and the remaining 12% are the alpha anomers. So there is a significant amount of beta furanose at equilibrium, but it's actually not even the major form of fructose. Nevertheless, that is the form that is necessary in order to couple with glucose in order to form sucrose. Okay, and I already said that the anomeric carbon is C2 rather than C1. So now, considering the stereochemistry of the glycoside bonds, since there are two glycoside bonds, we have to consider the stereochemistry with respect to each one. The linkage of the acetal oxygen to the glucose anomeric carbon, and the linkage of the acetal oxygen to the fructose anomeric carbon. So the terms we use for these are the glucoside bond, meaning the one to the glucose anomeric carbon, and the fructoside bond, meaning the one to the fructose anomeric carbon. So as you can see from the structure, the glucoside bond is alpha, and the fructoside bond is beta. Because once again, even looking at the final product in this case, on the glucose side, the acetal oxygen and the CH2OH at C5 are trans to each other, that's the alpha. But on the fructose side, the acetal oxygen and the CH2OH at C5 are cis to each other, and that's the beta on the fructose side. Okay, so as you could probably figure out, when you have two glycoside bonds, there are actually many stereochemical possibilities. They can both be alpha, one can be alpha, one can be beta, and vice versa, and both of them are beta. There's also the possibility now of having pyranoses and furanoses. Only one of these structures is sucrose. The alpha glucopyranose and the beta fructofuranose. Okay, so that's our brief foray into the chemistry and structure and chemistry of disaccharides. And we will conclude this unit by looking a little bit at polysaccharides.